Hi, everybody. If you have any questions during the talk, feel free to post them in the chat. It's not going to, let's say, annoy me. I'll follow the chat on Hopin, so feel free to ask questions. Now, before we start, I just want to warn you that the first part of the talk, it will kind of look like I'm talking about something completely useless. But bear with me till the end, because at the end we can see the power of the members through a looking glass. For people who don't know who I am, I'm a senior software engineer at KDAB, and I've also written a short book about functional programming in C++, which is available in several different languages. So let's start. Most of the software development is about composition. And I want to start with one person that I mentioned quite often in my previous talks. And it's not Dennis Ritchie. It's the guy on the left called Doug McIlroy. Now, obviously, everybody will recognize Dennis in this picture, but Doug, for some reason, is not as famous as Dennis is. If you don't recall the name, just remember this part of the code that I've shown at all different C++ conferences. And remember the story about calculating word frequencies that Donald Knuth implemented in several dozen pages in Pascal. And then Doug McIlroy gave a critique of the original implementation just by providing a 6-line implementation of the same problem. Now, this is something that is really astonishing, even if this solution is a little bit slower than the original one, etc. But Doug was, I would say, a genius who created the idea of what a Unix program should be like. So he wrote the rules, make each program do one thing well, and that one program's output should be piped to the next program as an input. And this is the philosophy that lived in Unix for a long, long time. And as we've seen in the previous example, it's quite a useful thing to have. So write small programs and make them composable. And this is the same with normal software design. You're just not going to have separate programs, but the idea of, let's say, most software design ideologies are to separate a huge program into small chunks that can be composed in some way. A recent tweet from Tony Van Erd, although I'd say most of the people wouldn't really agree with this one, but it's an amazing food for thought. 9 times out of 10, a for loop should either be the only code in a function, or the only code in the loop should be a function, or both. So the idea of this is, again, separating code into small chunks, with each chunk doing one thing really well, and then composing it in different ways, in this case, composing all the different functions with a for loop. In C++, we don't really have function composition. We can apply several functions to a value, so we can do something like call to string on something, and then use the result of that and pass it to a function called write. But we can't really write a composition of write and to string. Now, online we can find a dozen different implementations of a function that composes 2 functions for C++, and one of the simplest ones would be this compose function. So we accept f and g and create a lambda that accepts arguments, any number of arguments, and perfectly forwards them to f g of something. And now when we want, we can just use compose of 2 functions, and we are going to get a new function that is the composition of the previous 2 ones. Now, this is not the core language. this is something that we need to implement on the library level. And this is a strange thing to me to notice. Most of the languages talk about composing objects or composing functions, etc. But outside of functional programming languages like Haskell or Lisp, barely any language in the mainstream on the top 10 list supports any kind of composition with its syntax. Most of the compositions are done by the users or by developers manually. So let's move on to members. For normal functions, we've seen that we can call them f of something, of g of something, and we can compose them by creating a function that, like we've seen before. With members, we can't do something like this. So we cannot have a pointer to a member function and call it as if it were a normal function. We can't do something : to string and then pass it an argument. And this is something that should have been supported by the core language. But since it never got into the core language, the library working group was a little bit, let's say, naughty, and they decided to add something in the library space that will allow us to write something like this. And Daniela mentions that today in the evolution working group, there has been talk about this, and I definitely want to hear everything about it after this talk. So the library working group decided to treat member pointers just as normal functions. So when you think about it, any pointer to a member function accepts an implicit argument this and returns a value. So why shouldn't we treat it as a function? And they invented something called std invoke. It's a little bit uglier syntax than using normal call operator, but still we can now have the same syntax for normal functions, for any function object, any callable. So we can use this for member pointers to functions or to objects. So if we wanted to write a more generic compose function, we could just replace the normal call syntax with std invokes. When can we use pointers to member functions? We can use them in ranges accumulate. So for example, if we have a list of apartments and we want to accumulate all the monthly payments, which is a member of the apartment, we can just use ranges to accumulate everything and use the member function as a projection. So mind that this is not used for the folding or the accumulation function, but it's the last argument of accumulate, so the projection. If we didn't have the same setup, if we had apartments and inside of the apartments we have a tenant, and that tenant has a member called monthly payment, we could compose with our new compose function. We can compose accessor or getter for tenant and the getter for monthly payment inside of the tenant. But what about pointers to member objects? They also can be seen as normal functions. So if you pass in an instance of something t, you get an std string, so you get the value of that member. But that's not the only thing that we can see pointers to member objects as. We can also see them as something like setters. So a function that accepts an object, an instance of something t, a new value for that member, and it gives us an updated version of something t. So for normal members or member values or member objects, whatever you call them, we can see them as a pair of functions. One function is a getter and the other function is the setter. So let's try to make an abstraction over this idea, over this pair of getters and setters, and unite them into a single thing. Just like ranges are a united iterator and a sentinel, maybe we can achieve something really cool by uniting getters and setters. Now, setters are not really that great for composition, so we are going to change this a little bit. Just like ranges are not pairs of iterators, we are not going to use the obvious solution here to say getters and setters, but getters and updaters. What is the difference? An updater is not something that will take an instance plus a new value. It will take an instance of an object and a function that updates a value. So a function that accepts the old value and gives us a new one. So the idea is, when we have an updater, we have an old object. We take the value of a member that we're looking at and apply this function to it. It will give us a new value, and we are going to return an object with that updated value. So when we want to implement something like this, obviously we are going to create a generic class. There are dozen different ways to implement this. I decided to create something called typed property. The idea is that I want all the types to be known at compile time, so this is not going to support any, let's say, generic properties, but all the types needs to be known in advance so that we can do some static asserts, etc., so that we avoid long compilation errors. So object and value will be metadata about the class, so not something that can be used at compile time in template meta programs. And we are going to have two members, which will be mView, so the view function or getter, and mUpdate, which will be the update function. For view, it's quite trivial to implement. We just need to std invoke mView an object, and it will get us the value. For the update, quite a similar thing. We get the object and the updating function. What we are going to do, so I have a question from Puya. Is this going to be how to map classes to functional programming? I'm not going to answer that at this point, but kinda. And obviously Victor's answer is also spot on, at least to some extent. Now, to get back to this slide, for the update function, we are accepting a refref to object. If you're asking yourself why a refref to an object and then doing std move on said object, you can watch my previous talk at Meeting C++ Online from the last year on linear types and move-only type design. So the idea here is to avoid all the performance penalties of always returning new versions of objects, so to avoid any copies and similar things. So what we're going to do, we just need to invoke mUpdate and on object and update function. So this update member function is as trivial as the view member function was. The set function, which will be the classic and the traditional setter, is a little bit more complex, but still quite trivial to implement. Instead of passing a new function to the updater, we're just going to create a function that ignores its argument and returns a predefined value. So when this is invoked, what will happen? The old object, we will extract the old value from it, ignore that value, and this lambda will return whatever value we set. So it just ignores the previous value. In order to make this a function object, we can also create call operators on it. If somebody passes a single argument to this property, it's going to be treated as a view. And if it have two arguments, it will be either an update function or it will be a setter, depending on the type of the second argument. So I'm going to skip this slide. It's just some meta type trickery to extract for a pointer to a member, whether it is a member variable. It's going to extract the parent object, so the object that pointer belongs to, and the type of the member variable, so that we can use it inside of a constructor function for the property, typed property. For creating a typed property, consider this function like make pair or anything else, something that you can call without the need to specify the types for the typed property template clause. What this function does, since members can be seen as normal views, it's not going to do anything for the getter or for the view function. It will just pass in member as the getter function. But for the setter function, since so for the update, we don't really have the update function directly from the member, so we need to construct one. We said that pointers to members behave like normal setters, and we need to convert a normal setter to an updater function. And again, it's not anything, it's not really complex. We are just accessing a reference to that member and then invoking the updater function on it, and that's mostly it. So this is the first step. We have created an abstraction over something that looks like getters and setters. Obviously, this was the example only for pointers to member values, but we can also create this similar functions for normal getters and setters, so member functions. I'll leave that to you to implement. The question is now, since we've been talking about composition, how can we compose these things? So we need to define what view will a composition of two type properties be and what the update function will do. For the view, it should be fairly trivial. So just as a legend, we have a big object called outer. Inside, its member will be called inner, and we have a value which is a member of that inner object. So view function over the outer object is a function that gives us an instance of an inner object. And the same goes for the next one. View function of inner object will give us an instance of that value. So composing these two is quite trivial. We just need to match the codomain of one function and the domain of the second one. So when we compose, we are going to get let's say, a new function that takes an outer and gives us the value. For the updater, it's a little bit more complex. So we have an updater function that converts one value to another, and we need to construct a function that takes an instance of the outer object and just update a nested value inside of it. For the update function, what we can do, we can call the updater on the inner, and we can convert that into a lambda. So instead, just like we had originally done with the compose function for any arbitrary two functions in C++, we can do the same here. Instead of applying this to a specific value and to a specific instance of inner, we can just convert those two into a function, or let's say to lift it into a completely new function. So we can create a function that will update one inner into the other. And then we can use that function, the same principle, to update the outer object into, use that to update the value inside of an outer object, so doubly wrapped value. As for the implementation, just like we said, we are creating an auto update function, which will be a lambda that accepts an inner object, and then applies the updater for the inner object on that value that we've passed. And then this function has exact signature that we need to pass as the updater for the outer object. So what we got now, we have a function that returns us a value given the outer object, so the big object, and we have an updater for values inside of a bigger object. From this point on, we can even ignore that the inner object exists. In essence, this is kind of like if we had a direct pointer to a member for the value, because we've composed two different pointers from the outer class and from the inner class. So from this point on, when we have this composition, we can just forget that the inner object even exists. So let's see a few examples of how this can be used. So we have a monthly, which will be a composition of extracting the tenant from an object and then extracting monthly payment from the tenant. As for the greater than or shift right operator, obviously you can use any operators that you like. Shift operators are quite useful for this because we can switch the order if we wanted, for example, to have f of g of something and convert to g of f of something just by flipping to which side the shifting is performed. And then we call accumulate apartments initial 0. We use std plus for the folding function, and as before, we use this monthly thing as the projection on all the apartments. Because as a landlord, we don't really care about tenants or anybody else. We just care about the monthly sum that we're going to earn. If we realize at some point that we don't earn enough money, then we can just create a new apartment and use the same monthly thing. Say std move old apartment, so push old apartment to the updater, and provide a function that will increase the rent for 20%. And this is, let's say, the crux of type properties. A single object that can at both times push something and get a value. Now, there is nothing here that would convince you to actually use this yet, apart from that it's cool and it might be really efficiently used to confuse all your coworkers. But if we kind of move that to another level, you'll see that this can really, really be useful. So far, we've seen composition on functions and we've seen composition on properties. But we can compose all of those in a little bit different ways. Usually, when we talk about function composition, we have functions that need to satisfy the mathematical rules. So the first function's codomain needs to be the same as the domain of the second function. But let's see whether these functions are composable. If we have partial functions, so functions that return optional something, these functions are not mathematically composable, but if you've seen any of my previous talks, you know that this is composable just with a different definition of composition. If you remember monads, if you remember Cleasley composition, these two functions can be composed just not in a normal way. If we have vectors, the same story applies here. If we want to compose two different functions that take normal values and return vectors, we essentially just need to do transform and join. And this is something that we can do, if not with anything else, we can use Eric's range V3 for implementing something like this. Obviously, we are not going to have really vectors here, but any type of ranges. But I'll write vectors from now on to denote any collection in C++, any linear collection, sorry. So if we expand our definition of composition, we can switch from this example where we have a building with apartments, we have apartment with a single tenant and a single tenant that has a monthly payment. And we have the code that just composes these three type properties. And we can switch to a situation where each apartment can have multiple tenants, and each of those tenants pay the landlord a certain fee. And because we are a nice landlord, we can allow them even to have several monthly payments, for example, a weekly payment or something like that. So each tenant can have, again, a vector of monthly payments. And our accumulate code didn't really change. The only change that we have is that we added plurals in the variable names. So just by redefining what composition means in the case of a type property that has a vector or any other kind of ranges as its type, we can reuse the old once written code for something completely new. If we wanted to, for example, buy a jet ski, and we realize that we need to raise the rent, we can just create a new expensive building and apply payments to the old building and increase everything by 20% again. So let's present this graphically. If we have a building, so this big rectangle is a building, inside of it we have several apartments. Inside each apartment we have one or more tenants, and each of the tenants has at least one monthly payment. When we apply the apartments, we are just going to select all the apartments in a building. If we compose that with tenants, we are going to access all the tenants. And at this point, we don't really care about apartments anymore. In essence, now we just have a range of tenants collected from all the apartments in our building. The next step, pass that through monthly payments, and now we again get the exact thing that landlord wants. So a list of all the payments that we have inside of something. And just like before, we can accumulate all them and see how much we earn a month, and we can calculate and update how much more expensive the rent needs to be for us to buy a jet ski. Now the question is, can we move this even further? Instead of having monads like optional or vector or something like that, what would happen if we just use functions that give us futures? Again, in the same way, these functions are not mathematically composable, but if we use monadic composition or Kleisler composition, we can compose them as well. So the same code that we've had before, we can have futures of apartments, futures of tenants, futures of doubles. And when we compose all of those, we can get a future of all the payments inside of our building. And obviously, if accumulate supported futures, then this would be a normal accumulate of something which would return a future of double. But since accumulate doesn't really support futures, at least at this point, we need to implement our own, and the implementation could be quite trivial with coroutines. Just use the normal accumulate and sprinkle co-await on all the values that you are accessing. So this idea seems to be quite easily expanded. Now, I started this by saying that it's quite annoying to see something that is not supported by the core language. And it's kind of common thing to have in C++. We don't have variants as a core language feature. We have it as a library feature. We don't have pattern matching as the core language feature. We have it to some extent as something that we can create overloaded lambdas and similar things. And this is another of those things that are just not supported by the core language. The cool thing about something not being supported by the core language is that it forces you to implement it in the library. And when something is a library thing, you can do whatever you want with it. So as long as you can create something that works reasonably well and has a reasonably good syntax, you can redefine composition, you can redefine what accumulate means, you can redefine whatever you want. And the code that you've written once for normal values can start working for reactive streams or anything else. Another good thing is that this kind of eases up refactoring. If you decide to refactor your class so that several members that you have inside of it should be moved to another type, and that type should be a member variable inside of the previous class, you don't really need to change any of the callers. You just need to redefine the type property to be a composition of the two accessors instead of being a direct pointer to a member variable. This can also be quite easily expanded to filtering, to optional values, to have different accessors for vectors as a whole or vectors as we've seen as a range of values, etc., etc. And one thing that can be quite cool is that if you want to allow your customers to, let's say, write code, but you don't really want to allow them to write C++ proper, you can create things like these and put it inside of a GUI that will look essentially like the diagrams that we've already seen. And when people start composing those, they will have the graphical representation of all the things that their current query is going to affect. And before I end, as Victor mentioned, this is something that in, let's say, in literature, you can find under names of lenses. I didn't want to mention the name lenses before the end of the talk because I find one of the biggest hurdles for functional programming for normal developers is all the jargon that people have. So I'm going to continue calling these properties because we all know what properties are. And this is it. I'm open for questions.